Usually, when you talk about a system breaking down, whether it's, I don't know, a car engine stalling out on the highway or getting a medical diagnosis in some sterile clinic, there's this expectation of precision.
Right. Yeah. You want it to be clear.
Exactly. It's almost comforting, right? Like you break your arm, the doctor puts you in an x-ray machine, and there's that jagged white line right on the film.
Yeah.
The doctor just points to it and says, there is the problem. It's visible, it's categorized, it's this really clean narrative of cause and effect.
Well, it gives us a sense of control. I mean, when a system is legible like that, when it's binary like broken or not broken, we know exactly what tool to reach for to fix it. We're pretty much wired to solve problems we can clearly see.
But then you step into the world of planetary climate and these massive overlapping nested systems, and suddenly that diagnostic X-ray machine is just utterly useless. We're looking at a diagnostic landscape that is entirely murky, and that basically brings us to the core of our deep dive today. So, welcome to Crisis in Perception, where we examine the hidden systems shaping our world. Today, we are exploring a crisis not just of the environment, but like a fundamental crisis in human perception itself.
Yeah, we're looking at a system that has operated flawlessly for millions of years, and we are trying to understand how our modern architecture is just, well, colliding with it.
Specifically, we're going to explore the Earth's climate regulation system, which is centered on the cryosphere. For those who might not know, the cryosphere is just the scientific umbrella term for all the frozen water on our planet. So the glaciers, the sea ice, the permafrost, all of it. Yeah. Our primary guide for this journey is this deeply fascinating book called A World Without Ice by the geophysicist Henry Pollack. It also includes a foreword by Al Gore. We are using this text to conduct a systems-level examination of how Earth's ice functions as a planetary regulator and how human industrial systems have begun to override it.
And what makes this text so profound is the specific lens it applies. We aren't just looking at isolated, tragic environmental events like a starving polar bear or a localized flood.
Right, those are symptoms.
Exactly, or symptoms. We are looking at the incentive architecture of the modern industrial economy. We're examining how an economic system that operates on quarterly earnings and continuous growth is interacting with a planetary machine that operates on geological timescales.
Which is a massive paradox when you really unpack it. I mean, for millions of years, ice has stabilized Earth's climate. It created this incredibly specific, relatively stable climate envelope. And that stability is the exact condition that allowed human civilization like agriculture, cities, global trade to develop and flourish in the first place.
It's the only reason we're here.
Right. Yet the human industrial systems we built to survive within that envelope are now destabilizing the exact regulator that made our existence possible. It really begs the question, what happens when the planetary thermostat becomes the primary risk? Like, what happens when the regulator becomes the danger?
And that is the structural tension we really have to unravel today. You see, the system design of our planet depends on a very delicate balance. Ice reflects solar radiation to moderate temperature. Carbon cycles regulate the atmosphere through long-term geological sequestration. Water moves through this intricate hydrological cycle across the oceans, the air, and massive ice reservoirs.
But human economics operate on a completely different logic, right?
Totally different. Our systems treat fossil fuels, groundwater, all these finite resources as just easily extractable inputs for short-term expansion. Energy consumption is framed as progress, and it's completely decoupled from the physical constraints of the planetary systems it depends on.
It's just a fundamental mismatch of temporal frameworks. I mean, the climate system operates on planetary timescales, but human systems, we operate on electoral cycles, daily commutes, immediate consumption, and this creates a massive structural blind spot for us.
Yeah, we have a fundamental inability to see how our short-term actions are overriding a million-year-old machine.
So to fix that blind spot, to actually, see the X-ray, we have to start by understanding how the machine was built. Before we can grasp how we are breaking the thermostat, we need to understand how ice literally engineered the world you and I live in today.
The best place to start that engineering breakdown is with a physical property called albedo. Albedo is a term derived from Latin, and it simply means whiteness.
Okay.
In the realm of planetary science and climatology, it's a measure of the reflectivity of a surface. Everything on the surface of the Earth, like the dark soil in your garden, the green canopy of a forest, the deep blue of the ocean, it all reflects a certain percentage of incoming sunlight back out into the vacuum of space. But absolutely nothing on this planet does a better job of reflecting that energy than snow and ice.
I mean, if you've ever walked out of your house on a bright winter day right after a fresh snowfall, and you've been physically blinded by the glare. You have experienced the albedo effect firsthand.
Oh, yeah. It's intense.
And the mathematical scale of this effect on a planetary level is staggering. The notes from the source material honestly blew my mind. So, Earth as a whole reflects about 30% of all incoming sunlight back into space. But the polar ice caps, which cover Antarctica, the Arctic Ocean, and Greenland, they make up less than 10% of the Earth's total surface area.
Yeah, less than 10%.
But that tiny fraction of the planet is doing an overwhelmingly disproportionate amount of the heavy lifting for this reflection.
They essentially act as the planet's mirrors. To put some numbers to it, if a surface like a forest has an albedo of 15 or 20%, it means the vast majority of the sunlight hitting it is being absorbed.
And when light is absorbed by dark topsoil or deep ocean water, the energy of that light is converted into heat, right?
Exactly. But fresh snow can have an albedo of up to 90%. It bounces that solar energy right back out of the atmosphere before it ever has a chance to convert into heat. It keeps the energy entirely out of the planetary system.
I really want to dwell on this because I think it flips a common misconception on its head. I mean, I always thought of ice as a symptom of a cold environment. I assumed the logic was just, well, the North Pole is far away from the equator, so it gets less direct sunlight, so it's freezing, and therefore water turns to ice.
That's how most people think of it, yeah.
But what Pollack is arguing is that the ice is an active cause of the planet staying cool, not just a passive result of it.
That is the essential paradigm shift here. It is an active driver of the global climate, not a passive bystander. The initial setup is geographical, certainly. The poles are cold primarily because of the angle at which the sun's rays strike the spherical Earth.
Right, geometry.
Exactly. At the equator, the sunlight is hitting the surface nearly perpendicularly, delivering highly concentrated energy. But as you move toward the poles, the curvature of the Earth means those same rays are just grazing the surface at a really shallow angle, spreading the same amount of energy over a much larger area.
And that creates a natural temperature gradient. The book notes that the temperature drops roughly 1 degree Fahrenheit for every 70 miles you travel north or south from the equator.
Yeah. That initial lack of concentrated solar energy creates the baseline cold necessary for ice to form. But the moment that ice appears, its high albedo completely changes the game. It begins reflecting whatever weak, grazing sunlight does manage to arrive.
So it's feeding itself.
Precisely. By reflecting that energy away, the ice actively cools the surrounding air and water, which allows more ice to form, which then reflects more light. The ice is an active participant in its own chilling. It literally constructs its own environment.
And this active atmospheric dance is incredibly rare. To truly understand how unique Earth's ice is, Pollack pulls the camera way back and compares our planet to the icy moons of Jupiter and Saturn. And this was fascinating because extraterrestrial ice operates on entirely different physics.
It really does. When astronomers look at the icy satellites orbiting gas giants out in the outer solar system, they see two distinct types of surfaces. Some of these moons are heavily pockmarked with craters from ancient asteroid impacts.
Meaning they're pretty much dead rocks.
Exactly. That tells scientists the surface is dead. It's an ancient crust that hasn't changed in billions of years. But other icy moons have incredibly smooth, pristine surfaces, completely unblemished by craters.
Which means something is actively resurfacing them. Pollack uses this brilliant analogy. It's like a cosmic Zamboni just came through and smoothed out the ice.
It's the perfect visualization. If you go to a hockey game, this ice gets chewed up by the skates. Between periods, the Zamboni drives over the rink, laying down a thin sheet of liquid water that freezes into a fresh, smooth surface.
Right.
On these distant moons, there is a planetary Zamboni at work, but the mechanism isn't solar heat melting the ice. They are hundreds of millions of miles too far from the sun for that.
So what's melting it?
The heat that melts the ice comes from within, through a process called tidal heating.
Okay, when I first read tidal heating, I pictured ocean waves, but this is actually a gravitational phenomenon, right?
The underlying physics of gravity are similar, but the medium is solid rock and ice. Giant planets like Jupiter and Saturn have immense gravitational pulls. As their tiny moons orbit them, often in slightly elliptical paths, the gravitational force constantly changes. The giant planet is literally stretching and squeezing the solid mass of the moon, kneading it like dough.
That sounds violently powerful.
It generates unimaginable internal friction. All that stretching and squeezing of rock and ice deep inside the moon creates massive amounts of heat. That internal tidal heat slowly melts the bottom layer of the thick ice crust. And then The subsurface liquid water periodically erupts through geysers or seeps up through cracks to the surface, where it instantly freezes in the vacuum of space, creating a fresh, unblemished sheet of ice.
So on those outer moons, the ice is driven by the internal mechanics of gravity and planetary mass. The sun is completely irrelevant to their Zamboni, but Earth's ice is entirely the mercy of the sun, the atmosphere, and the oceans.
Yeah, we don't have enough tidal heating from our little moon to melt anything. Our ice is a surface phenomenon. It's entirely vulnerable to the climate envelope.
Which brings us to how Earth manages that climate envelope over millions of years.
Hmm.
Because the ice is so vulnerable, the planet needs a mechanism to prevent the atmosphere from getting too hot or too cold.
Yeah.
It needs a long-term geological thermostat. And this concept, which was pioneered by Earth scientist Jim Walker, completely rewired how I view the ground we walk on. I thought I had a basic grasp of the carbon cycle. Plants breathe in carbon dioxide, animals breathe it out.
Hmm.
But Walker's geological thermostat ties rock chemistry, rock formations, and climate together on a scale of millions of years. Let's walk through exactly how Earth regulates its own temperature.
Okay, so imagine the Earth's climate begins to stray. Let's say a period of intense volcanic activity pumps a massive excess of carbon dioxide into the atmosphere. Carbon dioxide is a greenhouse gas, so the planet starts running a fever. The global temperature rises.
Right.
How does a rocky planet cool itself down without a biological mechanism? It does it through a chemical process geologists call weathering.
And when I hear weathering, I usually think of wind eroding a canyon, but this is chemical weathering driven by the heat itself.
Exactly. Higher global temperatures generally lead to more evaporation from the oceans, which means more rainfall globally. When rainwater falls through an atmosphere rich in carbon dioxide, it becomes slightly acidic.
Like a weak acid rain.
Yeah. As this warm, slightly acidic rain hits the continental land masses, it increases the chemical breakdown of the rocks.
So the rain is literally dissolving the mountains.
Slowly, but yes. And as these continental rocks chemically decompose, the runoff flows into streams and rivers, carrying a much heavier load of dissolved minerals down to the sea. One of the most critical elements carried in this microscopic river cargo is calcium.
Okay, so the chain of logic is warmer planet leads to more acidic rain, which leads to more rock dissolving, which equals massive amounts of calcium flowing into the global oceans. What happens when the calcium hits the salt water?
A vital chemical reaction occurs. Once the calcium enters the ocean, it combines with the bicarbonate ions, which is essentially dissolved carbon, that are naturally floating in the seawater. When calcium and carbon bind together, they produce a compound called calcium carbonate.
Which is what shells are made of, right?
Right, marine organisms use this to build their shells, but even without life, it precipitates out of the water and eventually settles onto the deep sea floor as a solid layer of limestone.
So it's turning invisible atmospheric gas into solid rock at the bottom of the ocean.
Exactly. It is locking the carbon away in a geological vault. And here is the genius of the thermostat. As the ocean uses up its dissolved carbon to manufacture this limestone on the seafloor, it becomes undersaturated with carbon. To balance itself out, the surface of the ocean physically pulls more carbon dioxide out of the atmosphere.
Wow. So the ocean acts as a sponge, pulling the greenhouse gas out of the sky to replace what it just turned into rock? And as the carbon dioxide levels in the atmosphere drop, the greenhouse effect diminishes, and the planet slowly cools down. The fever breaks.
And the beauty of a thermostat is that it works in reverse, too. As the planet's surface cools, the global rate of evaporation drops, there's less rainfall. The chemical weathering of continental rocks slows to a crawl. The rivers deliver far less calcium to the sea.
Which means the ocean stops making limestone, and it stops pulling carbon out of the air.
Right. And because volcanoes are always slowly, naturally venting a baseline amount of carbon dioxide from deep within the Earth, that volcanic carbon begins to gradually build up in the atmosphere again without being scrubbed out by the ocean. The greenhouse effect strengthens, and the planet warms back up toward equilibrium.
It is an incredibly elegant, self-correcting chemical loop that has kept Earth's temperature relatively stable for billions of years. But the text highlights a massive, glaring vulnerability in this brilliant million-year system.
It does.
The entire chemical loop, the weathering, the rivers, the oceans, the limestone, relies on one very specific prerequisite: liquid water. Without rain to dissolve the rock or oceans to mix the calcium, the thermostat is completely, permanently broken.
And we don't have to look far to see the horrifying consequences of a broken thermostat. We have a planetary cautionary tale right next door: Venus.
Venus is often called Earth's twin. It's almost the exact same size, it has similar gravity, and it's made of a very similar chemical composition. It has mountains and valleys. It should, in theory, operate similarly to Earth.
But Venus is roughly 25% closer to the sun than Earth is. That slight proximity difference in the early days of the solar system meant Venus received just a bit too much solar energy. It was just hot enough that any liquid water that might have formed on its surface quickly evaporated into vapor.
And without oceans of liquid water, Venus couldn't run Jim Walker's geological thermostat. It had no mechanism to weather rocks or turn atmospheric carbon into limestone.
The volcanoes on Venus kept venting carbon dioxide, just like Earth's volcanoes do. But on Venus, the carbon had nowhere to go. It just stayed in the atmosphere, accumulating century after century, millennium after millennium. It created a runaway greenhouse effect, a feedback loop of unimaginable heat.
And the numbers for Venus today are genuinely terrifying. The surface temperature is over 850 degrees Fahrenheit. It's hot enough to melt lead on the surface, and the atmosphere is so crushingly thick with accumulated carbon dioxide that standing on the surface of Venus would feel like the pressure of being 3,000 feet underwater on Earth.
It is a stark reminder. Earth's average surface temperature has remained within the narrow, life-sustaining range of liquid water for most of its history entirely because our geological thermostat has never lost its water supply.
Okay, let's synthesize this. We have a planetary thermostat that utilizes chemical weathering over millions of years to prevent Earth from becoming Venus. It keeps the planet temperate. But even within that temperate safety zone, Earth isn't perfectly static. We have deep cycles of intense cold and relative warmth. And what the book reveals next is that these cycles, the rhythm of the ice ages themselves, literally forged the human species.
This is where we have to shift our perspective away from terrestrial chemistry and look up at orbital mechanics. The pacing of Earth's ice ages isn't random. It isn't driven by unpredictable volcanoes or random atmospheric anomalies.
Much bigger than that.
Much bigger. The deep rhythm of the ice is governed by 3 overlapping astronomical cycles, collectively known as the Milankovitch cycles.
Let's unpack these 3 astronomical pacemakers because it completely changes how you view a year on Earth. The first cycle Pollack details is called the tilt season.
We all know that Earth doesn't spin perfectly upright relative to its orbit around the sun. Its axis is currently tilted at an angle of about 23.4 degrees. This permanent tilt is the sole reason we have annual seasons. When the northern hemisphere is tilted toward the sun, it experiences summer. When tilted away, winter.
But the revelation here is that the tilt is not permanent. It's not locked in place.
Earth wobbles on its axis very slowly. Over a massive 41,000-year cycle, the angle of that tilt oscillates, shifting between a minimum of roughly 22.1 degrees and a maximum of 24.5 degrees.
So when the tilt is at its maximum of 24.5 degrees, the poles are pointed more directly at the sun during their respective summers. That means more extreme seasons, scorching hot summers, and brutally cold, dark winters. When the tilt relaxes closer to 22.1 degrees, the seasons are milder, the summers are cooler, and the winters are slightly warmer. That's the first pacemaker. A 41,000-year cycle of tilting. What is the second?
The second is called the distance season. The path Earth takes around the sun is not a perfect circle, it is an ellipse, a slightly stretched oval. But the shape of that ellipse is constantly changing due to the gravitational tug-of-war from other massive planets like Jupiter and Saturn.
Like a cosmic tug-of-war.
Exactly. Over a 100,000-year cycle, Earth's orbit stretches out into a more pronounced ellipse and then slowly circularizes again.
Which fundamentally changes our proximity to the sun at different times of the year. When the orbit is highly elliptical, there are times when Earth is significantly further away from the solar heat source. That's the 100,000-year orbital cycle, and the third pacemaker.
The third is known as precession. The easiest way to visualize this is to picture a child's spinning top. As the top spins rapidly, the central axis of the top doesn't stay perfectly still. It slowly sweeps out a wider circle in the air. Earth is doing the exact same thing in space. Our tilted axis wobbles in a circular motion over a 23,000-year cycle.
And what does that wobble actually do to the climate?
It changes the alignment of the seasons with the elliptical orbit. It dictates whether the northern hemisphere experiences its summer when the Earth is closest to the sun or when it is furthest away. It dictates which hemisphere gets hit with the most extreme combination of tilt and distance. Pollack uses an incredible auditory analogy to explain how these 3 massive abstract planetary motions actually trigger an ice age. He compares the Milankovitch cycles to an electronic music synthesizer playing 3 distinct continuous tones. I want you to imagine hearing a low hum, a mid-tone, and a high pitch all playing at once.
Right.
Most of the time, the wavelengths of these 100,000-year, 41,000-year, and 23,000-year cycles do not line up. It's just a gentle background cacophony. One cycle might be trying to warm the northern hemisphere while another cycle is trying to cool it down. They fight each other, and they mostly cancel each other out, resulting in a relatively stable, moderate climate. But eventually, the mathematics of the orbits dictate that the waves must sync up perfectly. The three separate synthesizer tones resonate together, producing a sudden, loud, dominant chord. And in climate terms, that chord strikes when the tilt, the orbit, and the wobble all align to achieve one very specific goal: minimizing the amount of summer sunshine hitting the high northern latitudes.
This is the counterintuitive genius of ice ages.
Oh, yeah.
It's not about how cold the winter gets. It's entirely about how cool the summer is.
Exactly. If the summer is cool enough, the snow that fell during the dark winter doesn't completely melt away. A thin layer survives into the autumn. The next winter, fresh snow falls on top of it. Year after year, decade after decade, the snow accumulates, compressing into thick continental ice sheets.
And the moment that ice starts surviving the summer, our old friend the albedo effect kicks in.
Yep, the accumulating white snow acts as a massive mirror, reflecting the already weakened summer sunlight away. This amplifies the cooling even further. The synthesizer chord triggers the onset of an ice age, and the albedo effect locks it in.
But the Milankovitch cycles are ancient. They have been pacing the Earth's climate for billions of years. However, the specific rapid rhythm of the modern ice ages, the ones that gave rise to humanity, didn't start until roughly 3 million years ago. To understand why, we have to look away from the stars and look at a tectonic event right here on Earth, the Panama Bottleneck.
This is a quintessential example of nested systems interacting, how geology alters oceanography, which alters the atmosphere, which dictates evolution. About 3 million years ago, the slow grind of tectonic plates pushed the ocean floor upward, creating the Isthmus of Panama.
Right, the land bridge.
Exactly. It created a solid land bridge connecting North and South America. Prior to this massive geological uplift, the Atlantic and Pacific Oceans were connected. Ocean currents flowed freely east to west through that tropical gap.
But when the landmass of Panama rose out of the water, it slammed the door shut between the oceans.
It completely severed the connection. The warm equatorial surface currents of the Atlantic, which had been happily flowing westward into the Pacific, suddenly hit a solid wall of rock. The water had to go somewhere, so the currents were forced to turn north. They became the precursor to the Gulf Stream, carrying massive volumes of warm tropical water far up into the North Atlantic, pushing all the way toward the freezing Arctic.
Wait, I have to stop you there. Sending billions of gallons of warm tropical water up to the Arctic triggered an ice age. That sounds entirely backwards. Wouldn't warm water melt whatever ice was up there?
It seems contradictory until you factor in the atmosphere. Warm water carries something critical with it: immense amounts of moisture. As that warm tropical water flowed north, it evaporated into the cooler northern air. It altered global atmospheric circulation, essentially pumping massive, unprecedented volumes of moisture into the sky above the far north.
Oh. And because the Milankovitch cycles were simultaneously playing their chord, ensuring the high latitudes were mathematically receiving less summer solar energy, all that massive new moisture didn't fall as warm rain.
It fell as snow, staggering, continent-burying amounts of snow. The new ocean current provided the raw material. The moisture and the orbital cycles provided the freezing temperatures. The modern cycle of rapid, massive glacial advances and retreats had officially begun.
And here is the ultimate realization, the aha moment of this entire text. This systemic ripple effect, from tectonic plates to ocean currents to orbital mechanics, didn't just change the weather. The closing of Panama and the initiation of these deep ice ages caused a profound climate shift thousands of miles away in Africa.
The reorganization of global ocean currents led to a severe drying and cooling effect across the African continent. The dense, lush, unbroken forests that covered much of the landmass began to die back. They receded, giving way to vast open grasslands and savannas.
And living in the canopy of those shrinking forests were our ancient hominid ancestors, the Australopithecines. For millions of years, they had lived a relatively stable existence, relying almost entirely on the dense trees for food, for safety from predators, for shelter. Suddenly, their entire world vanishes. The trees die. They are violently forced out of the canopy and into the open, unforgiving grasslands just to survive.
The evolutionary pressure was absolute. The physical traits that served them in the trees were no longer enough. They couldn't outrun the predators on the savanna, and they couldn't rely on the easy foraging of the forest. They had to adapt their behavior. They had to invent.
The harsh, changing environment literally forced early hominids to develop the cognitive leap necessary to fashion stone tools. It sparked the beginning of the Paleolithic period. It drove the evolutionary leap from Australopithecus toward the modern human genus, Homo. The rhythm of the Ice Ages is the literal author of human ingenuity. We are, quite literally, children of the ice.
We are. And for almost 3 million years, humans existed as passive passengers on this planetary ride. We simply adapted to the whims of the ice. When the glaciers advanced and absorbed the oceans, sea levels fell, exposing land bridges that allowed humans to migrate across continents. When the ice retreated, we adapted again. We were pawns in a vast system governed by orbital physics and tectonic geology.
But that human ingenuity, the very tool set born from the crucible of the Ice Ages, eventually led us to harness fire, agriculture, and ultimately industrialization. Which brings us to a profound turning point in the narrative of the planet, the Anthropocene.
Yeah, the era of humans.
Exactly. This is the moment when the passengers in the back of the plane realized they could pry open the cockpit door and start blindly pulling levers. We transitioned from passive organisms adapting to a climate to active, deeply clumsy managers of the entire planetary thermostat.
To understand the sheer scale of our clumsiness, we have to look closely at the physical mechanism of the greenhouse effect. It is a concept that is universally referenced but widely misunderstood.
Pollack uses an analogy in the book involving a microwave oven, and it finally made the atmospheric physics click perfectly for me. Let's unpack this slowly. The sun sends massive amounts of energy to the Earth every second, mostly in the form of visible light. It's the light we can see with our eyes, all the colors of the rainbow. And our atmosphere is mostly transparent to this visible light, right?
That is correct. Our atmosphere is composed of about 99% nitrogen and oxygen. These gases are essentially invisible to the incoming short-wavelength visible light from the sun. The solar energy passes right through the atmosphere unimpeded, strikes the surface of the Earth, and physically warms the land and the oceans.
But the Earth can't just endlessly absorb that heat, or the planet would continuously heat up until the oceans boiled away. It has to maintain an energy balance by sending that heat back out into the cold vacuum of space. But here's the catch. The Earth doesn't glow. It doesn't send the energy back out as visible light.
Because the Earth's surface is vastly cooler than the 10,000-degree surface of the sun, it radiates energy back outward at a much longer wavelength. It radiates invisible infrared energy, which we feel as heat.
And this is exactly where the microwave analogy comes into play. If you put a plate of food in a microwave and turn it on, the machine generates specific electromagnetic waves.
Yeah.
Those waves pass completely harmlessly through the air inside the microwave, and they pass right through the glass plate. But they are specifically tuned to be absorbed by the water molecules inside your food.
Right.
The water molecules absorb that specific wave energy, they start vibrating rapidly, and they convert the wave into heat, cooking the food.
Yes. In our atmosphere, certain trace gases act exactly like the water molecules in your food.
While the nitrogen and oxygen ignore the heat, the trace gases catch it.
Precisely. Greenhouse gases like carbon dioxide, methane, and water vapor are completely transparent to the incoming visible light from the sun. But when the warmed Earth tries to radiate its invisible infrared energy back out to space, those specific complex greenhouse gas molecules intercept it. Their molecular structure is perfectly tuned to absorb that outgoing infrared frequency. They absorb the energy, vibrate, and convert it into trapped heat within the lower atmosphere.
It functions like a one-way mirror for thermal energy.
Yeah.
The sunlight comes in freely, but the resulting heat is physically blocked from leaving. But I have to push back here, because this is where skepticism often arises. When people hear that human trace gases are altering the planet, the immediate counter-argument is, hasn't the Earth always experienced massive natural disruptions? What about volcanoes? Don't massive eruptions pump out millions of tons of greenhouse gases and totally alter the climate without any human help?
They absolutely do alter the climate, and Pollack dedicates significant time to exploring this. Volcanic eruptions can have devastating, instantaneous climate impacts. For instance, in 1815, the cataclysmic eruption of Mount Tambora in Indonesia injected millions of tons of sulfur dioxide high into the stratosphere. It created a reflective aerosol shield that physically blocked incoming sunlight.
It triggered what historians call the year without a summer in 1816, causing widespread crop failures and famine across North America and Europe.
And similarly, the eruption of Krakatoa in 1883 threw so much particulate dust into the upper atmosphere that it altered the color of the sky globally. The English painter William Ashcroft famously spent months painting the brilliant, terrifyingly blood-red Chelsea sunsets over London, all caused by volcanic dust from the other side of the planet.
Wow.
Krakatoa's disruption of the atmosphere also contributed to brutal winters globally, including the legendary blizzards of 1888 that wiped out livestock across the American Great Plains.
So nature does violently disrupt the climate. The system isn't perfectly stable on its own.
Nature disrupts it, yes, but we must recognize a crucial physical distinction in the timescales. Volcanic cooling is a profound but very short-term phenomenon. Gravity eventually wins. The ash and sulfur particles physically fall out of the atmosphere over the course of a few years, and the climate quickly rebounds.
Okay, I see.
On the opposite end of the spectrum, the natural geological warming and cooling driven by Jim Walker's limestone thermostat takes millions of years to slowly adjust carbon levels.
So you have the flashbang of a volcano lasting 3 years, and the slow grind of continental weathering lasting 3 million years.
Exactly. What humanity is currently doing by extracting and burning fossil fuels operates on an entirely unprecedented middle gear. It is an anomaly in the physical history of the planet.
We are essentially acting as an artificial supervolcano, but instead of blocking the sun with ash, we are exclusively pumping out the invisible insulating gas. We are taking billions of tons of carbon that the geological thermostat painstakingly scrubbed out of the air and locked underground hundreds of millions of years ago, and we are violently throwing it back into the atmosphere in the span of a single century.
And we aren't just guessing about how unprecedented this is. We have the physical receipts. We can literally read the ancient history of the Earth's atmosphere written in the ice itself.
The ice cores. I knew scientists dug up ice, but the logistics of the Lake Vostok operation are staggering. Tell us how this actually works.
Lake Vostok is one of the most extreme environments on Earth. It is a massive subglacial lake, roughly the size of Lake Ontario, buried deep beneath the Antarctic ice sheet, right under the Russian Vostok Scientific Research Station. To access the history locked above it, an international team of scientists spent years engineering a way to drill down through 2.5 miles of solid frozen ice.
And the reason they drill there is because of how ice forms in the deep interior of Antarctica. It doesn't snow very often, but when it does, the temperature is so brutally cold that the snow never, ever melts. It just piles up, layer upon layer, year after year, century after century.
It creates a perfect vertical timeline. As the new snow piles on top, the immense crushing weight physically compresses the older snow underneath into solid glacial ice. But as it compresses, it traps tiny, microscopic bubbles of the ambient air between the snowflakes.
So the ice isn't just frozen water, it's millions of microscopic glass jars holding the air from the past.
They are literal time capsules of the ancient atmosphere. Scientists carefully extract these massive cylinders of ice and bring them into ultra-clean laboratories. By crushing the ice in a vacuum and chemically analyzing the air that pops out of those tiny bubbles, they can measure the exact concentration of greenhouse gases that were in the sky on the day that snow fell.
Amazing.
The Vostok core provided a continuous, year-by-year physical record of the atmosphere stretching back 450,000 years.
450,000 years of hard data. And what does the timeline reveal when you look at it?
It reveals the heartbeat of the planet. The data perfectly maps onto the Milankovitch cycles we discussed. It physically proves that carbon dioxide levels naturally rise and fall in perfect lockstep with the orbital ice ages. The data shows the natural boundaries of the planetary thermostat.
But then you look at the very top of the ice core, the snow that fell in the last 2 centuries.
The modern data is a vertical line. The current levels of atmospheric carbon dioxide and methane observed in the newest ice are completely off the charts. They dwarf anything the Earth has experienced in the last 500,000 years. The massive spike corresponds exactly, year for year, with the dawn of the human industrial revolution.
Which brings us to the concept of the Anthropocene, a term popularized by the Nobel Prize-winning atmospheric chemist Paul Crutzen. He argued that the Holocene epoch is over, and we have entered a new geological epoch defined entirely by human activity.
The age of humans. The thesis is that humanity has grown so massive and our industrial systems so hungry that we have fundamentally wrested control of the planet's core operating systems away from nature. We now dictate the carbon cycle through fossil fuels. We dictate the nitrogen cycle through artificial agricultural fertilizers. We manipulate the hydrological cycle by damming nearly every major river on the globe. The collective footprint of human engineering is now the dominant geological force on Earth.
And reading through the text, there's this incredible, almost painful historical irony regarding the timeline of our understanding. We often act like climate change is a recent complex discovery that snuck up on us in the late 20th century. But in 1859, an Irish physicist named John Tyndall set up a laboratory experiment and became the first person to successfully measure the heat-trapping ability of carbon dioxide gas. He definitively proved the physics of the greenhouse effect over a century and a half ago.
And in that exact same year, 1859, a man named Edwin Drake traveled to Titusville, Pennsylvania, and successfully drilled the very first commercial oil well.
1859. The exact year humanity discovered the physical mechanism of our own potential ruin is the exact same year we began pumping the fuel to accelerate it. We have known the basic physics of this problem since the dawn of the oil age. So the obvious question is, if the data from the Vostok ice cores is so undeniably clear, and the physics of the greenhouse effect have been understood since 1859, why is global society struggling so profoundly to react?
This brings us to the core thesis of the book, the crisis in perception. We are failing to react because we are facing a profound structural conflict between how human neurology evolved to perceive threats and the invisible reality of geological timescales.
Pollack calls it an evolutionary blindness. And when you think about it, it makes perfect logical sense. Think back to those Australopithecines we talked about, the ones forced out onto the African savanna by the Ice Age. Their brains, which are the foundational architecture for our brains, evolved under intense pressure to prioritize immediate, localized, visible threats.
Right, survival.
Yeah, if there's a lion hiding in the tall grass, your brain floods you with adrenaline so you can run. If a rival tribe approaches, you react. If the local watering hole dries up, you move.
Exactly. Our neurological reward systems and threat detection centers are heavily biased toward the here and now. Natural selection did not equip human beings with a built-in global vision or a deep, intuitive, intergenerational memory. We simply were not wired by evolution to feel an emotional panic about what the global average temperature model might look like a century into the future. It doesn't trigger our fight-or-flight response.
It requires a level of abstract, systemic thinking that feels fundamentally unnatural to a primate brain. Pollack points out how cognitively difficult it is for a normal person to connect their mundane, everyday actions, like turning up the thermostat in your living room on a chilly morning, or driving a gas-powered car to the grocery store, with the melting of the Arctic ice cap thousands of miles away. The cause and the effect are separated by massive, incomprehensible distances in both physical space and time.
And compounding this hardwired evolutionary blindness is a psychological phenomenon Pollack terms the illusion of insignificance.
Oh, this is a powerful observation. When you turn on the news and watch raw footage of a Category 5 hurricane leveling a coastal city, or a massive earthquake swallowing buildings, or a tsunami erasing a shoreline, humans feel incredibly tiny. We feel entirely fragile and powerless against the raw, majestic forces of nature. So, on an intuitive level, it feels incredibly arrogant and counterintuitive for the average person to internalize the idea that tiny humans could somehow break a planet.
It defies our physical common sense. When we look at the ocean, it looks infinite. But what our intuition fails to appreciate is the sheer compounding scale of the collective. A single human is entirely insignificant to the planet, but 7 billion humans, armed with millions of massive fossil-fueled machines, actively moving mountains to extract coal, clear-cutting continental rainforests for cattle, and paving over millions of square miles with dark asphalt, that collective synchronized force now mathematically dwarfs the power of plate tectonics and volcanoes combined.
We have outscaled the Earth's natural systems, but we still feel small in our daily lives. Now, to be entirely fair to you, the listener, the difficulty in perceiving this crisis isn't solely due to our natural psychology. It's not just a biological accident. The source material explicitly points out that this natural blindness was deliberately amplified by institutional forces. And I want to make sure we strictly and impartially report exactly what the text claims here without taking sides.
Absolutely. According to the book, the crisis in perception was intentionally deepened through a deliberate amplification of scientific doubt. The author outlines how powerful entities within the carbon-based energy industry, Pollack specifically names Peabody Coal and ExxonMobil, alongside political factions like the George W. Bush administration, invested heavily in public relations campaigns designed to label established climate science as unsettled or as junk science.
The text argues that these campaigns exploited the public's lack of systemic understanding to manufacture a controversy, thereby maintaining the economic status quo. And the book takes time to detail several of the specific contrarian arguments that were widely amplified to confuse the public dialogue. Let's walk through those objectively, strictly based on how the text addresses them. The first is a fascinating argument. The claim that other planets in our solar system, specifically Pluto and Mars, are also experiencing global warming.
The contrarian logic presented is quite straightforward. If distant planets like Pluto and Mars are currently warming up, and there are obviously no humans driving SUVs on Mars, then the cause of the warming must be the sun itself. Therefore, the warming on Earth is a natural solar phenomenon, not human-caused.
So how does Pollack's text refute that planetary argument?
The author breaks down the specific astronomy of those planets. Pollack acknowledges that Pluto did recently experience a warming of roughly 3.5 degrees Fahrenheit. However, he points out that Pluto's orbit is vastly different from Earth's. A single year on Pluto takes 250 Earth years to complete. Its warming is driven by its own extreme, decades-long seasonal shifts and massive changes in its surface albedo as it moves along a highly elliptical, stretched-out orbit.
Okay, what about Mars?
Similarly, the text notes that Mars is warming not because of the sun, but because massive global dust storms recently cleared out of its atmosphere, leaving a more transparent sky that lets more local sunlight hit the dark Martian soil.
And the text points out that the basic math of solar output just completely destroys the sun hypothesis.
It does. Pollack notes that if the sun's radioactive output had suddenly increased enough to warm Pluto by 3.5 degrees, keeping in mind that Pluto is 40 times further away from the sun than the Earth is, then the Earth, being so much closer, would have simultaneously warmed by more than 18 degrees Fahrenheit. Our oceans would be boiling.
Yeah, that makes sense.
Furthermore, the text cites satellite measurements taken over the last half of the 20th century, which actually show that total solar radiation hitting the Earth was trending slightly toward cooling during that period, not warming.
Okay, another prominent contrarian theory the book mentions is the cosmic ray connection.
This is a highly complex alternative theory suggesting that cosmic rays, high-energy particles shooting in from deep space act as atmospheric seeds, creating clouds in Earth's sky. The hypothesis is that when the sun is very active, its solar wind creates a magnetic shield that blocks these cosmic rays from hitting Earth. Fewer cosmic rays mean fewer clouds. Fewer white clouds mean a lower planetary albedo, which lets more sunlight in, warming the Earth.
So it's an intricate way of saying it's still the sun's fault, just indirectly through magnetic cloud seeding, not direct heat.
Exactly, but again, the source text refutes this by pointing to the instrumental record. The empirical data of the sun's activity over the past 50 years simply doesn't support a massive, sustained increase in solar wind that would be necessary to drive the rapid compounding warming we are seeing today. The text concludes that these contrarian theories, while creative, serve primarily as systemic distractions from the stark, proven reality of greenhouse gas physics, the physics Tyndall proved in 1859.
So synthesizing all of this, we have a delayed neurological perception. We have deep psychological barriers that make us feel small. And according to the text, we face institutional obfuscation designed to sow doubt. Because of all these nested layers of blindness, humanity is actively ignoring the physical feedback loops we are triggering. The gradual changes are quietly building up in the background, and the planetary regulator, the ice, is slowly turning rogue. Which brings us to a terrifying concept: tipping points.
Right. In the study of complex systems, tipping points are critical thresholds. They occur when a system passes from one stable mode of behavior into a completely different state. The hallmark of a tipping point is that the approach to it is often slow, incremental, and almost imperceptible. But once the threshold is crossed, the transition is sudden, violent, and often irreversible.
Pollack uses the absolute most perfect analogy for climate tipping points I have ever encountered. He compares it to the agonizing process of paying off a 30-year home mortgage. Let's really dwell on this, because anyone who has ever owned a home will feel this in their bones.
When you first take out a 30-year mortgage and start making payments, the progress feels incredibly, insultingly slow. For the first 10, 15, even 20 years, almost your entire monthly payment goes directly toward paying off the interest generated by the massive loan. The actual principal, the underlying massive debt you owe the bank, barely shrinks at all.
You look at your bank statement after 10 years of writing these massive painful checks every single month, and you realize you've paid off maybe 10 or 12% of the actual house. The numbers barely move. It feels like a completely static, unchanging system. You feel trapped in the interest phase.
Exactly. But the math of a loan is a complex curve. Eventually, you reach a crossover threshold. Around year 20 or 21, the ratio shifts, and your monthly check is finally split evenly between the interest and the principal.
Right.
That crossover is a tipping point, even though it passes quietly without fanfare. But beyond that specific point, the system changes behavior. The reduction of your unpaid balance suddenly accelerates. The principal begins to vanish rapidly, month after month. And finally, you hit the ultimate tipping point. The abrupt, instantaneous transition to a new financial state where the loan is paid off completely, and you suddenly have no mortgage payment at all. Your financial reality alters overnight.
Our global climate change is currently stuck in the slow interest phase of the mortgage. It feels incredibly incremental to our primate brains. The global average temperature rises by a fraction of a degree. Sea levels creep up an inch or two over a decade. We look at the data and we intuitively feel like we have plenty of time to figure this out, but we are rapidly approaching the principal payoff phase, the cliff edge. And it is the ice itself that is driving us toward that cliff through brutal physical feedback loops.
Let's examine the mechanics of those loops, because this is the exact moment where the regulator becomes the risk. Feedback loop 1 is albedo reversal.
The great white planetary mirror turns dark.
Right. As the ambient temperature of the Arctic warms due to greenhouse gases, the vast sheets of summer sea ice begin to melt and shrink. As the white ice vanishes, it exposes the dark, deep ocean water that was hidden beneath it. As we know from the albedo effect, dark water does not reflect sunlight. It absorbs it aggressively. The ocean acts like a sponge for solar radiation, warming the water significantly.
Which means when the long Arctic night returns and winter comes, the ocean is holding so much residual heat that it takes vastly longer for the water to cool down enough to finally freeze.
Exactly. The refreezing process is delayed by weeks or even months. Because the freezing season is shortened, the new layer of ice that forms over the winter is significantly thinner than it used to be. So, when the next summer arrives, that structurally weaker, thinner ice breaks up and melts much faster, exposing even more dark water for an even longer period of the summer.
It's a compounding loop.
It is a vicious mechanical cycle that accelerates itself entirely independently of human emissions. The more ice you lose, the faster you lose the rest.
And that rapidly warming Arctic Ocean triggers the second domino, feedback loop 2, permafrost methane.
If you look at a map of the far north, vast expanses of land in Canada, Alaska, and Siberia are covered in permafrost. This is ground that has literally been frozen solid year-round for tens of thousands of years. But it's not just frozen dirt. Locked inside that deep frozen ground are massive, unimaginable quantities of organic material, essentially the ancient remains of dead plants and animals that froze before they could decompose.
But as the Arctic warms up from the dark water albedo effect, that ancient frozen ground begins to thaw out, and all that organic material finally starts to rot.
And as it rots in the wet, waterlogged, boggy conditions of the thawing tundra, it is consumed by microbes that release massive amounts of methane gas as a byproduct. Methane is an incredibly potent greenhouse gas. It is vastly more efficient at trapping heat than carbon dioxide over the short term.
So the warming climate melts the permafrost, the rotting permafrost releases methane, the methane traps more heat in the atmosphere, which in turn melts even more permafrost. The system ratchets itself upward in a continuous loop.
Yeah, precise.
Okay, here's a question I had while reading the book that totally scrambled my brain. Could global warming actually cause catastrophic freezing in certain parts of the world? Because the text brings up feedback loop 3, the Gulf Stream shutdown.
Yes, and this highlights the deeply counterintuitive nature of fluid dynamics and ocean currents. If you look at a globe, Western Europe, places like London and Paris, are at roughly the same high latitude as central Canada and the frozen expanses of Siberia. Geographically, Europe should have a brutal, freezing subarctic climate.
But it doesn't.
No, Europe is kept unnaturally mild and temperate by the Gulf Stream, a massive, powerful ocean current that transports warm tropical water from the equator all the way up into the North Atlantic.
It's essentially a massive planetary heat pump keeping Europe warm.
But that pump doesn't run by magic. It is driven by a very specific mechanical engine located in the extreme cold of the Arctic. When the warm, highly salty water of the Gulf Stream finally reaches the frigid Arctic, the water rapidly cools down. Cold water is physically denser than warm water, and salt water is denser than fresh water.
Okay, physics 101.
So this cold, salty water becomes incredibly heavy. It literally sinks. It plummets thousands of feet to the dark bottom of the ocean like a massive underwater waterfall, and then flows back south along the deep sea floor.
So millions of gallons of dense salt water sinking to the bottom creates a massive vacuum at the surface, which is the mechanical engine that physically pulls the warm water up from the equator to replace it.
Exactly. The sinking is the engine. But now, remember the melting sea ice and the thawing permafrost we just discussed? All that rapidly melting ice dumps massive, unprecedented volumes of fresh, unsalted water directly into the Arctic Ocean. Furthermore, the thawing permafrost increases the flow rate of massive northern rivers, dumping even more fresh water into the sea.
And fresh water is significantly less dense than salt water. It's more buoyant, it floats on top.
Precisely. The surface of the North Atlantic Ocean is becoming warmer and drastically less salty. It is becoming too buoyant. The water stops sinking. And the physics are inescapable. If the dense water stops sinking at the pole, the underwater waterfall ceases, the vacuum disappears, and the entire Gulf Stream stalls out. It shuts down.
Oh, wow.
Without that continuous transport of equatorial heat, Western Europe could suddenly plunge into a deep, enduring, agriculturally devastating chill, even as the global average temperature of the rest of the planet continues to rise.
And we know this isn't just theoretical modeling because it has happened before. The text mentions a period called the Younger Dryas.
Yes, the geological record shows that roughly 12,700 years ago, as the last ice age was ending, a massive glacial ice dam broke in North America. It sent an absolute flood of fresh meltwater pouring into the North Atlantic. The fresh water stalled the ocean currents exactly as we just described, and the average temperatures in Europe rapidly plummeted by about 10 degrees Fahrenheit.
So a localized change in the salinity of the high Arctic Ocean completely altered the survival conditions of an entire continent. That is the terrifying cascading reality of nested systems. A melting glacier in Canada freezes a forest in France. And then there's the ultimate consequence of all this melting ice, the one everyone thinks about, sea level rise. But Pollack notes there is a massive public misconception regarding how melting ice actually affects the oceans, and he clarifies it brilliantly using the ice cube analogy.
It is a very simple physics experiment you can do in your kitchen. If you take a glass of water and drop a large ice cube into it, the water level in the glass immediately rises because the submerged portion of the ice physically displaces the water. But if you let that glass sit on the counter, as that floating ice cube completely melts, the water level in the glass does not change by a single millimeter.
Wait, so floating ice melting doesn't raise the sea level at all?
The physics dictate it cannot. The vast expanses of Arctic sea ice at the North Pole are already floating on the surface of the ocean. They are already displacing their weight in water. If every square inch of the floating Arctic sea ice melts tomorrow, it will not add a single drop of volume to the global ocean level. Similarly, the massive land masses of Antarctica and Greenland are ringed by colossal floating ice shelves. Some of these shelves are the size of entire European countries, extending hundreds of miles out over the ocean. When those floating shelves crack, break up, and melt, they do not directly raise the sea level either.
Then why are climate scientists constantly warning us about catastrophic sea level rise from melting ice?
Because of what is located behind those floating shelves. The massive floating ice shelves act as physical, structural buttresses. They are the cork jammed tightly in the bottle. They use massive friction to physically hold back the millions of cubic miles of glacial ice that are resting solidly on the bedrock of the continental landmasses of Greenland and Antarctica.
So the land-based ice is the real threat.
Yes. When the floating sea shelves break away and vanish, which satellite imagery shows is happening at an alarming rate right now along the Antarctic Peninsula, the massive land-based glaciers behind them suddenly lose their structural support. The cork is removed.
And they start moving.
Fast. The glaciers speed up. They begin to literally sprint toward the coastline, lubricated by meltwater underneath them. And when millions of tons of land-based ice physically slide off the bedrock and plunge into the sea, that is the equivalent of dropping a massive, brand new ice cube into an already full glass of water. That displaces water, and that raises the global sea level.
And the text makes a chilling point. We don't even need all that land ice to physically melt to cause a global catastrophe. It doesn't need to melt. It just needs to slide off the rock and into the water. We're already seeing early signs of bulk ice sliding directly into the ocean vastly faster than it is being replenished by snow.
And we have a terrifying historical proxy for how fast this can happen. About 120,000 years ago, during a naturally warm interglacial period before the last deep ice age, scientists have analyzed fossilized coral reef records. Those ancient corals indicate that global sea levels rose an astonishing 8 feet in the span of just 50 years.
8 vertical feet in half a century.
Yes. That kind of violent, rapid speed cannot be generated by the slow, gradual melting of ice from warm air. It is physically impossible. That speed can only be caused by the extremely rapid, catastrophic sloughing of bulk continental ice sliding directly into the sea. If an 8-foot rise happens today, the implications from modern coastal infrastructure, from the subways of New York City to the floodplains of Bangladesh to the ports of Shanghai, are completely unimaginable. We are talking about the displacement of hundreds of millions of climate refugees.
Which naturally begs the most frustrating question of this entire deep dive. With all these feedback loops spinning up, with tipping points looming, and historical precedents of catastrophic sea level rise, what is stopping immediate, aggressive global action? Why are we paralyzed? This leads us to the final analytical segment: inertia, uncertainty, and the illusion of waiting.
The delay stems directly from the conflicting timescales we established at the beginning of this conversation. Human political and economic institutions prize stability, predictability, and incremental, manageable change. But we are currently dealing with a planetary physics system that possesses a massive, almost incomprehensible amount of inertia.
Pollack uses an aircraft carrier analogy to describe this inertia, and it perfectly captures the momentum of the problem.
Think about the physical dynamics of a massive nuclear-powered aircraft carrier steaming full speed ahead across the Pacific. If the captain perceives a threat and orders the helmsman to spin the steering wheel hard to the right, the ship does not instantly pivot and change direction like a sports car. The mass of the ship is too great. It plows straight ahead on its original, dangerous course for thousands of yards before the massive momentum is finally overcome, and the rudder slowly, agonizingly begins to turn the bow.
The Earth's climate system has that exact same physical momentum. Climatologists call it climate commitment.
It is a terrifying reality of the physics. Even if humanity achieved an absolute political and technological miracle today, if every single factory, car, and power plant on Earth was shut down, and we completely halted every single molecule of greenhouse gas emissions globally this very second, the carbon dioxide we have already pumped into the atmosphere over the last century will not vanish. It will linger there, trapping heat, for over 100 years before it is slowly dissolved into the oceans or sequestered by rocks.
So the momentum of the aircraft carrier is already carrying us forward. We are locked in.
We are committed to unavoidable structural change. Even in that magical, impossible scenario of zero global emissions starting today, the Earth's atmosphere holds so much accumulated energy that it would still inevitably warm by about another full degree Fahrenheit by the end of this century. We are fundamentally locked into a continued loss of Arctic sea ice, the shrinking of mountain glaciers, and some degree of rising sea levels, regardless of what we do.
Okay, I have to play devil's advocate here for a moment, because this is the exact argument where global policy debates become incredibly fierce.
Yeah.
If you are telling me that the warming is already locked in by physics, and if you look at the scientific models like the Intergovernmental Panel on Climate Change models, which project future warming of anywhere between 3.2 and 7.2 degrees Fahrenheit by the end of the century, that is a massive, highly imprecise spread. If the science is that uncertain about the outcome, shouldn't we just wait until the scientific models are more precise before we completely overhaul and potentially wreck the global economy?
That is the single most common argument used to justify political inaction, but it fundamentally misinterprets where that uncertainty actually comes from. The wide range in those IPCC models, that massive gap between 3.2 and 7.2 degrees of warming, is not because the atmospheric physics are flawed. It is not a symptom of scientific uncertainty. It is a symptom of social uncertainty.
Social uncertainty. You mean the uncertainty is us?
Exactly. Climate models don't just run on physics. They have to run on scenarios of human behavior. The supercomputers have to guess how many human beings will exist on the planet in 50 years and how those humans will choose to live. For example, demographers estimating the global population by mid-century project, it will be somewhere between 8 billion and 11 billion people.
That is a difference of 3 billion people. To put that in perspective, 3 billion people was the entire global population in 1960. That is an entire mid-century Earth's worth of humans, just acting as a statistical margin of error.
Precisely. Imagine trying to model the energy demands of an extra 3 billion people. 3 billion extra people consuming energy, growing food, demanding transportation, building infrastructure. The physicists know exactly, down to the decimal point, how efficiently a molecule of carbon dioxide traps infrared heat. What they do not know is whether humanity will collectively choose a massive transition toward clean, renewable energy and population stabilization, or if we will choose a business-as-usual path of burning coal and oil to fuel a rapidly expanding population.
I see.
The massively wide range of the climate forecast simply reflects the massively wide range of our possible political and economic choices.
Okay, so the core science is sound, but our future behavior is the ultimate wild card. But even still, if we are faced with that massive social uncertainty, isn't waiting to see what happens the most prudent move?
No, it isn't. And Pollack's text cites the work of Robert Lempert and his colleagues at the Rand Corporation to explain exactly why waiting is a trap. Waiting for uncertainty to disappear before taking action is essentially making a choice to passively endorse the dangerous status quo. It is an illusion of safety. The social uncertainty is never going to magically disappear because we simply cannot predict human technological innovation or geopolitical shifts 50 years into the future.
So if we can't wait for certainty, what is the alternative mechanism for making decisions?
Lempert advocates for a framework called adaptive management. Because the future is deeply, inherently uncertain, we shouldn't paralyze ourselves trying to predict a single, perfect, long-term outcome with absolute precision. Instead, we must choose actions today that are robust and beneficial across many possible different futures. We make decisions based on the current data, we implement policies to aggressively reduce emissions and build infrastructure resilience, and then we actively, continuously monitor how this complex planetary system reacts.
And we course correct as needed.
Exactly. You learn how complex systems work by interacting with them and watching them behave. When the climate system or the economic system deviates from your goal, you adjust your policy. But you do not stand paralyzed at the steering wheel of a speeding aircraft carrier just because you don't know the exact wind speed 100 miles over the horizon. You turn the wheel now and you adjust as you go.
And this brings us back perfectly to Al Gore's foreword in the book, which attacks the fundamental premise of my devil's advocate question. It attacked the idea that we must constantly choose between saving the planet and saving the economy.
Gore explicitly calls it a false dichotomy, and Pollack reinforces this systemic argument by looking back at the 2008 global financial crisis.
The concept of nested systems rears its head again.
Think about how the 2008 economic collapse actually happened. It did not happen overnight out of nowhere. It was preceded by decades of slow, largely unnoticed, incremental erosion of fundamental financial regulations, oversight, and risk management. Toxic subprime assets were allowed to build up silently within the deep plumbing of the system, all while the surface-level quarterly earnings looked fantastic.
Right.
Everyone ignored the structural rot until a critical threshold was crossed, the feedback loops of panic kicked in, and the entire global economy collapsed suddenly.
It is the exact same mechanism as the 30-year mortgage analogy.
Yeah.
It is the exact same mechanism as the climate tipping points.
Precisely. The climate crisis is following the exact same systemic pattern as the financial crisis. It is a slow, largely unnoticed erosion of the physical fundamentals of the planet, the melting ice, the rising carbon, that will inevitably lead to a sudden catastrophic collapse of the systems we depend on. Treating the global economy and the planetary environment as separate, competing, isolated interests guarantees that we will inevitably fail at both.
Because of the same system.
They are inextricably linked. They require the exact same systemic overhaul, a shift away from risky, short-term, extractive logic toward long-term, stable sustainability.
So let's bring all of this massive complexity together. What an incredible journey. We started by looking at the cryosphere, the ice, not as a passive, dead backdrop of winter, but as the active, highly reflective architect of our global climate. We saw how the ancient Milankovitch orbital cycles and the tectonic closing of the Panama bottleneck created the specific, rapid rhythm of deep cold and warmth that dried out the African forests and literally forced our early hominid ancestors out of the trees, sparking human ingenuity.
Ice is the great planetary regulator. It actively maintained the delicate temperate zone that kept the planet stable enough for agriculture, cities, and modern civilization to flourish.
But now, armed with the ingenuity born from that ice, we find ourselves completely trapped in this crisis of perception. We view the world through the tiny, immediate, localized window of a human lifespan. We are worried about our quarterly stock returns, our daily commute, the localized weather over our house. Meanwhile, entirely accidentally, through the sheer compounding scale of billions of people operating massive industrial machines, we are blindly pulling the deep levers of a planetary thermostat. We are actively turning the regulator itself into the ultimate risk.
To truly grasp the scale of what we are doing and how quickly we are doing it, the author shares a profound perspective from geologist Don Eicher. He proposes visualizing deep time through a cosmic calendar.
I love these temporal scale models because they shatter our human bias. Walk us through Eicher's calendar.
Eicher asks us to imagine compressing the entire 4.56 billion year history of planet Earth into a single standard calendar year.
Okay, so January 1st at midnight is the violent formation of the Earth from a cloud of dust.
Right. And the planet is so volatile that the oldest solid rocks we can find don't even form until late January. The very first primitive single-celled life appears in the primordial seas sometime in late February.
What about the dinosaurs? We always think of them as ancient history.
In the context of the Earth, they are relatively recent. The dinosaurs don't even show up on the calendar until mid-December, and the massive asteroid impact that wipes them out entirely occurs the day after Christmas, December 26th.
December 26th. The dinosaurs dominated the planet for a massive stretch of time, but on this scale, they are wiped out just a few days before the year ends. So when do humans finally arrive on the scene?
The very earliest man-like creatures, the ones adapting to the newly formed ice ages, don't appear until the late evening of the very last day of the year, December 31st. Human civilization is a blink. The entire Roman Empire, from its rise to its fall, rules the Western world for exactly 5 seconds, from 11.59.45 to 11.59.505 p.
5 seconds for the entire span of the Roman Empire.
Christopher Columbus reaches the Americas just 3 seconds before midnight, and the human industrial revolution, the exact moment we started digging up ancient coal and oil, inventing the steam engine, and fundamentally altering the chemical composition of the atmosphere, begins about 1 single second before midnight.
1 second.
In the last single second of this entire planetary year, humanity has wrested control of the global carbon cycle, violently spiked the planetary temperature, and begun irreversibly melting the million-year-old ice caps that birthed us.
That leaves me with one final, deeply provocative thought, something for all of us to mull over as we wrap up this deep dive. If our species has only been managing this planet for the last single second of its existence, and we are already systematically dismantling the massive physical ice thermostat that kept us alive, does saving our climate ultimately require more than just new technology? Does it actually require us to completely change our perception of time itself? Are we as a species actually capable of learning to think like a planet before the planet decides it no longer has room for us?
It is the ultimate question of the Anthropocene. It demands a fundamental evolutionary shift, from being passive passengers exploiting an endless environment to becoming truly responsible managers of a finite, nested system.
Thank you all for joining us on this incredible journey. If you value this kind of deep systems-level analysis, please consider supporting Crisis in Perception on Patreon. This project is free and publicly accessible, and your support helps fund the time, tools, and research behind it.
You can also check out our visual mini-explainer of the Cryosphere, which is linked in the description below.
And if you enjoy this kind of systemic breakdown, please like, subscribe, and comment with books or topics you'd like us to explore next. Until next time, keep looking past the surface.